Um, Welcome to another iOS seminar series. So today we're happy to have Professor Chih-Yu from Department of Electrical Engineering, National Hsing University. Professor Wen received his bachelor and master degree from National Chung University, and then he went to University of Wisconsin and received his second master degree and PhD degree. All the degrees are in electrical engineering. In 2006, he came back to Taiwan and joined the Department of Electrical Engineering, National Hsing University, where he is currently a lifetime distinguished professor. Professor Wen won 2 Best Paper Awards, and he also received National Innovation Awards for his contribution of the remote rehabilitation and smart medical devices in quite a few years in 2016, 2018, 2019, 2020, and 2021. That's why I need a cheat sheet, right? So he has been an associate editor of IET signal processing for more than 6 years. Today, we're happy to have Professor Wen to share his recent work on genetic algorithm to allocate resources in container-based cloud. So without further ado, let's welcome Professor Wen for his talk.
Thank you very much, Professor Xu, for the introduction. And hi, everyone. It's my great pleasure to be here and talk about the container-based heterogeneous cloud. And the first part of the talk, I will focus on the technical issues and also with the design issues. And the second part of the talk, I will try to explore the problem background and also discuss the optimization strategy and also try to introduce the algorithm design. And the last part of the talk, I will try to emphasize or describe the framework characteristics and also try to evaluate the system performance and outline the future research direction. Okay, so I use the smart city systems, try to have an idea about the IoT and the smart system applications. So as we can see, the cloud computing is the core part of this kind of systems, and use this part we can try to develop the very added applications. And from the infrastructure of these smart systems, okay, as we can see, we have several layers, okay, and also we have the edge computing, fog computing, and also with the cloud computing. And also we have the many IoT devices to consider with the heterogeneity of the IoT devices. So based on this system and also with this infrastructure, I will try to consider the following issues. And we will try to connect with the cloud, edge, and IoT continent. Use this part, try to develop the so-called applications to achieve this part. However, in order to achieve this goal, we have to consider several issues. For example, with the architectural issues, and also with the organization issues, also with the service and the applications. So the next part, I will try to use the following perspectives, try to discuss the challenging issues. The first one, as we can see from the previous infrastructure, you can see so many components, subsystems in these smart city systems. So we may have to consider with this one as the heterogeneous cloud environment, because many applications is provided by the various providers. And also we have to consider the service and application infrastructure. As we can see, this kind of complicated system, we may consider as this part to develop the so-called, the first part will be so-called monolithic application. Okay, the first part of application structure. And the other part we may consider as the so-called microservice architecture. Okay, so the first architecture actually is try to have this kind of united and independent program front, and also use this part to have this kind of information developed by these independent applications. And for the microservice architecture, actually, we just split up the applications to many distributed and independent services. So in this part, we try to emphasize or highlight the maintainability and also with the scalability in this system. And also this operation or implementation for this kind of microservice architecture is from top to bottom. Okay, so this will be the technical issues and also with the architectural issues in this case. And in this part, we have used the shopping example to describe this kind of the scenario and also explain how the microservice work. So in the first case, this will be the monolithic case. Okay, so with the payment, shopping cart, and the inventory, they just merge as together to implement as a whole system. And however, in the microservice architecture, we may have this kind of payment, shopping cart, inventory as the individual components. And each part actually they have its responsibility or functionality, and also have its own database to perform a specific function for this part. So this will be the basic idea for the monolithic application and also with the microservice applications. So in order to achieve this kind of complicated systems, so we have to kind of think about what are the technical challenges for this part. So in this case, we may face the resource allocation or management. We may face the scheduling with the multitask. And also we may consider the heterogeneity of the IoT service or devices. Okay, so we may consider use the way to implement this kind of microservice such that we can achieve the cloud IoT and to the edge continent. So we may have consider with maybe use the container, Docker, Kubernetes for the management or organization with these microservices. So in the following case, I will try to have the basic idea for this part. For the container, okay, so the container basic is the example trying to implement this microservice because it's a standard software unit to implement this one. So the software developer can just focus on their development, okay, not to worry about the system or environment. And for the Docker actually is the environment with this kind of software source platform to implement this container. Okay, and also we will use several organization or management tools, for example, for the Apache, Mesos, Docker Swarm, or Kubernetes, try to organize or manage these container-based applications. In this talk, I will focus on the Kubernetes as an example to assess or to find out the feasibility of the proposed system. Okay, so this will be the basic idea for this part. And in this case, I will try to, from the technical issues and the challenging issues, try to write up the first part of the talk. For the first part, we try to kind of have the basic idea of the microservice and also with the organization, also with the resource allocation. So the best way of the architectural design principles, we may consider two perspectives. One perspective is trying to organize or manage the container. Okay, so for this part, we'll try to use this way to manage the container-based applications, consider with the Docker organization, use this way to achieve the application code. And the other ways, we have so many IoT devices and also with the sources. So how to organize this resource? Okay, so we will face the resource allocation problem. So we'll try to develop so-called optimization strategy to do that. However, as we know, the resource allocation problem actually is the NP-hard problem. Okay, so for the NP-hard problem, it's very complicated and also challenging. And the GA algorithm actually is considered is the one of possible and effective way to solve this kind of problem. So in this case, we will use this one as the basics and also use an enhanced GA algorithm try to solve this optimization problem. So I will introduce this one later, non-dominated sorting genetic algorithm too. Okay, so this was a basic idea. We solve this problem from two perspectives. One is about the organization, the other will be the optimization strategy. Okay. So I use this summarized table trying to explore the problem background for this problem. Okay, so the first part, let's take a look at this architecture with the cloud. Will be the single cloud or multiple clouds or heterogeneous cloud or with the multi-heterogeneous cloud. So we just extend the environment to more complicated case, or we try to deal with the multiple heterogeneous cloud. And also we will deal with the optimization problem. Let's take a look for this case. So generally we can categorize it into 4 groups. The first one may be the machine learning base, or the greedy base, or the NSGA2 base, the GA base, and also always the cumulative base for this part. So in this case, we will try to solve the problem and focus on the management issues and also with the objectives issues. So we try to deal with the, for example, with the microservice placement, also with the resource allocation case. And also we use the following matrix indication to assess the performance of the proposed system. For example, with the resource utilization, how about the system reliability, and also with the communication overhead in this part. So in this talk, we will try to consider this part and also try to tackle the heterogeneity for this case, okay, with this cloud environment. Okay, so this will be the basic idea for this talk, and try to solve this problem based on the optimization strategy and try to perform the resource allocation. Okay, so the second part of this talk, I will try to introduce the basic method and also with the system framework, design principles for this part. Okay, so the first part is the system framework. System framework is trying to tackle the cloud environments from 2 kind of perspective or point views. First one, we try to develop the analytical architecture, or try to consider the relationship with the workload, cloud service, and also with the hybrid clusters, with the interaction with the hybrid clusters. The second part, we will try to specify the workflow with the framework. Okay, consider the users, clusters, database, and with the measurement. Okay, so this will be the 2 viewpoints for this system framework. The next part, I will try to use this figure to describe the architecture with this part. So we have the workload here, the request here, and with the basic cloud service. Then the framework actually consists of 4 components. The first one will be the monitoring unit. The second one will be analysis unit. The third one will be the microservice placement unit. The last one will be management unit. Okay, so for the monitoring unit, you will monitor the utilization of the resource. And for the analysis unit, you will try to describe the status of the clusters and microservice, and also try to analyze the performance of the microservice. And the optimal placement will be based on the optimization strategy. We will try to use the algorithm result, try to place the corresponding microservices. And the last one will be the Kubernetes API, try to base on the placement strategy to do the task assignment. Okay, so they just interact with the hybrid clusters to perform the workload deployment, okay, to achieve this the analysis framework. So this first part, I will try to use this way to describe the architectural design for the system framework. And the second part, I will use this workflow to kind of with the connection between each units. Okay, so I just divide this workflow into 3 stages. Stage 1, okay, so the users put a request. So the management unit receive the request. They just perform this workload to these clusters. Then this monitoring unit just monitor the utilization for the clusters, and also monitor the status, and also with the microservice. Then they just get the data to the store in the measurement database. And the analysis unit just download the recorded data based on this way to analyze the behaviors of the microservice, and also try to describe the performance with the clusters. Then the optimal placement unit, they just perform the optimization strategy based on this loaded analysis data. they just perform the microservice placement. And for this Kubernetes management unit with the API, to use this one to place the corresponding microservice to achieve the load balancing idea with this part. So this will be the whole picture with this workflow. Okay. Then the problem will be how to allocate this resource and how to reduce the computation overhead. So this will be our two objectives. Consider the framework, consider with the complexity of the system in the cloud environments. We just specify two objectives. One is try to maximize the resource utilization. The other will be try to reduce the computation overhead. Okay, so this will be the trying to allocate this kind of information or resource for the microservices. So the objective one, okay, sorry.
I remember in the table, the objective is another, the third one reliability.
Right.
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 And, I didn't see it. I didn't. So it's how to model reliability, and it seems that it didn't show up in this
right.
problem.
So for the reliability will be, I use the I just introduce this way. So I just skip. Okay, I just skip here. Okay, I just consider with this here. We have three components for the object two. Also, we have the unvariable probability here to consider the connection or the variability with the service, and also use this way to describe maybe the nodes or the service may experience unvariable or failure during that part. So we use this one as the way to indicate the so-called reliability way. Okay, thank you. So okay, let's go back to the objective one with the resource utilization. I use the so-called service dominant load idea, try to maximize the load of the all resource types. So I use like the weight average way to consider the variance data deviation with the resource. So the denominator will be the a variable resource capacity with this one will be the memory and this one will be the CPU. And with the numerator will be the request amount of the memory and the request amount of the CPU resource. That one. Okay, so this will be the basic idea, and I try to kind of average or to avoid the disparity for this part. So we use this scale to kind of have the weighted average to consider the deviation with the memory and the CPU. Okay, so this will be the first part. Try to maximize the resource utilization. And the second part, so we use three components to indicate to emphasize the retransmission mechanism for the system. So we use the failure probability or unvariable frequency, and also consider the network distance between two nodes with the microservice, and also consider the communication amount between the two nodes with this microservice. So use this way we try to minimize, reduce the network overhead or transmission overhead. Okay, so this will be our two objectives for this part. Trying to use this way to specify the program for this one. Okay, so this will be our optimization model. This one will be the balance part for the cluster. Try to balance the part, and the other will be the overhead. Okay, so try to use this way and consider try to with the certification with the resource. Okay, so this will be the available capacity with the memory and the CPU, and this will be the request by the microservice in each cloud and the nodes. Okay, so this will be the overall picture for our allocation model. Okay. Okay, so let's move forward to another stage with the algorithm design. So we explore the problem background, also we discuss the optimization strategy. Now let's take a look at the algorithm design for this part. So we propose, this work proposed the so-called MOMA algorithm, or multi-objective microservice allocation algorithm. So based on the enhanced GA algorithm, or we call the non-dominated sorting GA algorithm. Okay, try to this one. Because the GA algorithm have a problem because they may suffer from getting trapped in the local optimal problem. So in this case, we try to use so-called non-dominated sorting, try to extend this adaptability with this part. And with this case, we may just describe the following genetic algorithm in later. However, before introduce this presentation, I will focus on the NSGA2. I will introduce the NSGA2 first, then let's go through the presentation of the chromosome. So for the NSGA2, this algorithm, I just use these figures try to describe the so-called non-dominated sorting. And they also have this kind of terminology called the Pareto from. Actually, the Pareto actually is the Italian economist. They just have the so-called 80-20 rules. Okay, so say many outcomes, just roughly 80% of consequences come from the 20% of the causes. Okay, so this will be the best idea with this so-called non-dominated sorting. So in the following figures, in the bottom left figures, we can see the two features. Try to maximize these two features, F1 maximization, maximize, F2 maximize. So actually this gray pink area will be so-called Pareto from, because they are maybe the best solutions for this one. And in the other way will be the minimization, so this will be the Pareto from for this solution. And in this case, let's consider the 4 possible solutions. So with the maximization feature. So as you can see this part, we can have the solution A, maybe the best solution in this case. So we call this A will be the non-dominated solution. And the solutions B, C, D, we are called dominated solutions. Okay, so in this case, will be the first part, we do the non-dominated sorting in this case, based on our optimization strategy or objectives. Then we have this Pareto from. However, we like to have good spread between the solutions. So we may use so-called the crowding distance sorting, try to have the good spread and the diversity with these solutions. So we will have the crowd distance sorting later to get the final generation. So here we have the parents and the offspring here. Then based on the non-dominated sorting, with the crowd distance sorting, then we get the final generation here. So this was this part with the NSGA2. Okay, so this will be the whole idea with the NSGA2. Now let's go back to see the chromosome representation. So we have several ways to describe the clusters and the microservice. So with the cluster 1, assume we have 2 nodes, node 1 and node 2. And node 1, they may perform the several microservice. So MS, for example, MS5 will be the operation with the microservice 5 via the node 1 in cluster 1. So with the binary encoding scheme, we just have the connection with the relation between the containers, nodes, cluster, microservices. So use this way to represent the allocation and also with the chromosome, with the genetic algorithm. So for example, we have the chromosome here, we have 7 microservices. Then they will assign, for example, with the MS1, actually is performed via the node 1 in cluster 1. Okay, so this will be the chromosome representation for this part. And the other way to describe this part will be the displacement operators for the genetic algorithm. We have so-called the crossover and the mutation. And for the crossover, okay, so this will be the basic operation with the crossover. They have the operator, consider the combination with the parents, and also with the beta or beta parameters. They will consider as the random number parameters, and also with a constant, try to describe the alliance with the parents or not. For example, if we get a larger number of eta, okay, then the eta will be the, for example, with the larger number. So here will be the almost approaching to 0. So the beta approach to 1. So this will be more like the just combination with these two parents. Okay, so this will be the way to describe the so-called alliance with the parents and with the offsprings. Okay, so we use this way to generate the two springs individuals by the so-called simulated binary crossover operator with this probability. Okay, so this will be the one displacement operator. Okay, and the other operator will be the mutation. Okay, use this one. Consider with this part as the to generate the diversity. So with the insertions, also maybe we can use the so-called deletions with the DNA. Okay, for example, with these two, this for 2-2 indicate the microservice 7. They just have the new service performed with the node 2 in cluster 2. Use this way, and also with the deletion of the task will be here with the microservice 1. So they just delete while node 2 in class 2. So use this way to generate the operation with the microservice, and also consider this one as the assignment with the nodes and the cluster. Okay, so based on this operation and also the background initialization, so I try to introduce the so-called MOMA algorithm. The first part, let's take a look at the inputs and outputs of this algorithm. So the inputs will be considered with the cloud environment, with the cluster, with the host, microservice, with the network distance, and also with the communication, okay, with the between two nodes with the microservice. And this part will be the initialization. So based on our operation with the population size, offspring size, or with the mutation probability, cross probability, and also with the termination criteria, try to set up the GA environment with this part. And the output will be our Pareto from. Okay, Pareto from based this part. Okay, so this will be the basic input output for this part. Then let's go through the whole procedures with the workflow of the algorithm. So we just invite the workflow into 3 stages. The first part, let's initialize the population. Then, based on this terminology criterion, okay, basic setup for the operator with the crossover, the mutation. Then we generate our offspring. Then we perform the so-called non-dominated sorting to consider with the ranking and also calculate the crowding distance. Then based on this part to generate the Pareto from. Okay, so this will be the basic operation for the MOMA algorithm. Okay, so in this case, we almost finished the introduction with the basic idea with the technical challenges, and also we introduced the basic idea with the program and also with the algorithm design. So let's take a look at the characteristic or behaviors for these systems, and also consider the performance comparison between other existing words. So first part, I will introduce the experimental environment, and also we'll try to establish several cloud applications. Try to use this way to assess the system performance. Okay, then use so-called empirical analysis, try to get the whole picture of the performance. So this will be our experimental environment. Okay, so we have 3 clusters. Okay, so the cluster 1 will be the one workstation with the Raspberry Pi. Okay, the other clusters, we just use the PC and with the Raspberry Pi. And the cluster 3 will use a PC with the Jetson Nano, NVIDIA Jetson Nano. Okay, so as you can see, they have 3 different clusters with the devices, and actually we may consider this one as the 3 heterogeneous clouds with this one. So we have multiple heterogeneous cloud in this case, try to organize the resource and also try to analyze the behavior for this part. Okay, and this will be the the test applications. So I use 3 heterogeneous cloud applications. Try to use this way to describe or to characterize the behavior of the system. So the first, we may consider this one as the Kubeflow. Okay, the Kubeflow actually is the program model. It just built on the Kubernetes. Okay, so this case, they choose this way, trying to handle the basic operation with this software. And the second applications we call the sock shop. Actually, this one is widely used in the microservice environments, okay, because they just implement this one and for testing and implementation. And also, we may use the real scenario request to test these structured applications. And the third one will be the HX Foundry, okay. So this will be the open source platform. We use this one and also use the Raspberry Pi as the edge devices and also use the sensor. Try to collect the temperature and the humidity information to run this IoT service. Okay, so we have 3 different applications to test our system. Okay, so in order to have this one, let me just use so-called empirical analysis, try to have the workload profiling. Basic idea with this part. So we inject the input with the applications and also consider the iterations and also consider the workload durations for the input. Okay, so in this case, we just have the 1 to 10 user requests and continuous for the 450 seconds in this duration. And also we run 20 iterations for the result. Okay, and also we consider this one. So we workload here and just inject the workload and consider and monitor the performance of this one. In order to have a better realization with these applications, so we have this visualization part for this one. So we use Prometheus, this one as the platform to monitor the cluster memory usage, the CPU usage, and the file system usage. Okay, so use this one. And also we use the so-called locust, the framework, try to implement the user request here. Okay, so to do the load testing in this case. And under this case, we just summarize the performance with these 3 applications. So the first column here will be the CPU usage. So as you can see, we have 3 applications. And also with the containers, actually try to implement the small service, okay, with the controller, with the environment, or with the cache, okay, and also with the HX Foundry, the sock shop, okay. The first column will be the usage of the CPU, and the second column will be the memory. The third column will be the interaction with the communication amount of communication between the nodes and by the microservices. Okay, the unit will be the CPU, will be the number of cores, and the memory will be the number of megabytes, and the interaction will be the gigabytes per second. Okay, so use this way to basic idea with the microservice in each component. Okay, so the next part, I will try to compare the performance with our optimization strategy. So this will be the basic idea with the workload profile in this case. And here will be the implementation for our optimization strategy here. So we may consider with the default Kubernetes, the Google Kubernetes default system with the greedy algorithm, and also with the so-called multi-optity algorithm, and with the proposed system. So we use this way, try to consider based on the environment, okay, with the workload and the hardware heterogeneous clouds, try to compare with the following analysis with the resource utilization, computation overhead, and reliability with this case. Okay. So let me just introduce the 3 algorithms here. The first one will be the Kubernetes default algorithm. So this will be the basic figure for the Kubernetes default algorithm. To have the clients, we have the load balancers to complete assign the service with the POP. The POP will be a set of microservices. a set of containers. And with the multi-operator algorithm, we may consider this one. We have two clusters. There will be cluster 1 and cluster 2. And we have two nodes here, two virtual machines here, and 3 virtual machines here. And also we have 3 microservices here, 1, 2, 3. So they just describe the interaction. And for the multi-operator algorithm, they try to consider the association with the cluster nodes and also with the microservices. Okay, so this will be the operation with the multi-operator. And the grid-based, they just consider the problem, find out the solution, best solution. For example, they find out this one will be the best clusters to perform the test. They just hold the workload in these clusters. Okay, so this will be the grid-based heuristic algorithm will be the basic function for this one. Okay, so let's try to compare these 4 algorithms based on our environment and also with the heterogeneous cloud applications. Okay, so the first part, let's consider the resource usage with the applications. Okay, so we assume the failure rate will be this range, random pickup from this range, and distance, network distance from the 2 nodes based on this the range. And as you can see, the first column will be the focus on the computation resource allocation. The second column will be the memory allocation with this part. And with respect to different application, the first one will be the HX foundry. The second row will be the sock shop, and the third row will be the Kubeflow. So as you can see, the y-axis with this resource allocation analysis. So the y-axis will be the standard deviation of this operation with this microservice assignment. Okay, so as you can see, the Kubeflow it has the lowest deviation compared with the sock shop and the HS foundry. Okay, so this is because the characteristic with the Kubeflow application, because they just use the constant request and the demand from the users. So that's why it has the lowest deviation compared with the sock shops and HX foundry for this case. Okay, and also consider with the algorithms. Okay, so as we can see, the blue one, the top one will be the greedy one, So it will be the greedy and the greedy, and the lowest one, the middle one will be the Kubernetes and also with the multi-operator, and lowest one will be the MOMA, the proposed system, MOMA system. Okay, because the greedy, they just consider with the microservice, because they just focus on this interaction. They didn't consider the interactions, okay, between these 2 clouds or clusters. So this will be the reason why it has the largest deviation. Okay, and Kubernetes and the multi-operator, they just consider the resource utilization. Okay, so this will be the middle case. And for the MOMA algorithm, actually we consider the heterogeneity for this one. So we have more comprehensive consideration for the performance. So that's why we have the lowest deviation in these 3 applications. Okay, so this will be the resource usage. Okay, so with the network communication overhead, so as you can see, we can use these figures to describe the behaviors with the proposed system. The x-axis will be the number of requests for the user request from 1 to 10. And the y-axis will be the transmission overhead. And also we consider with the 4 algorithms. So with the lower number of user requests, as you can see, the 4 algorithms actually have similar performance for this one. However, when we increase the number of the user requests, okay, so with the, for example, for the Kubernetes and also with the multi-operator, because they just consider the behavior of the components. So let's go back to the, back to the description of the algorithm. So this part, they have basic consideration. So there's association between the containers, nodes, and also with the clusters, and also with the Kubernetes. Also, they have to consider with these resource connections. So that's why they have larger computation overhead here. And with the greedy, because they just place the best solution, put a whole microservice in one cluster, in the same cluster. Okay, so that's why they have the lower computation overhead. Okay, and also our case, because we have the performance with the structure 2. So that's why we have the similar and also with the better efficiency compared other 3 related words. Okay, I will use this design brief to wrap up the discussion and today's talk. So firstly, we have the framework and also service consideration. So the first part of the talk, we consider the challenging issues and the architectural issues. Then we will go through the problem with the problem background and also consider the development of the algorithm. Then we set up so-called empirical environments and also with the workload analysis, try to assess this algorithm performance. Okay, so in the future world, we will try to, because we use the we use the CPU and the memory. We haven't used the GPU resource consideration, so in the future, we may consider with the GPU resources. And also, we may consider as the theoretical bounds, try to analyze, for example, with the delay and with the response time for the microservice. So this is our future goals, try to use this way. And I will show you about the future trend for the cloud computing. So from the 2025 to the 30, so this will be the possible deviation or the future trend for the cloud computing. So with the multi-cloud, with the AI, and also with the edge computing, and also with the cloud-native development approach, and also with the cloud orchestration. So here we use the Kubernetes as the basis with the orchestration. So what is the best way? Maybe use the lightweighted orchestration strategy, maybe the best way for the IoT devices or applications. So this will be another issue. And also, we haven't touched the security issues with the blockchain and also security measures. So this will be our future directions to have this kind of, to solve this issue and also advance this field. Okay, so this is pretty much the talk of today, and thank you very much, and hope you can enjoy this talk and also have some sharing with the questions. Thank you.
Thank you, Professor Wen. Any question from the audience?
I have one from page 18. Thank you. Thank you for an excellent talk. It's very interesting. Although I'm not really network expert, but still, can I ask a question on page 18, where you have a problem formulation, I think. Right here. Yeah, so my question is that in your objective function, you have 3 different types of factors, right? Failure, distance, interaction. So they are all on different scales, right? So the first one, probability, right? So it could be something between 0 and 1. Distance is not sure how you measure the network distance as a hop, right? Hop. So it's it should be an integer, right? Then the interaction would be some real number. So all these are mixing up in the objective function. So are on different scales. Will that affect will one will dominate the others? That's my question.
Yes.
Yeah.
Yes, thank you for Professor Liu's questions. Yes, for the failure, we just used so actually it's very excellent questions because we consider the applications and also we set up the range for the testing. Actually, we use the, oops, okay, here, okay. So this will be the range for the failure case, and also with the distance, and also with the number of the amount of communications. Yes, because with the empirical test, we have this kind of the units for this one, for the CPU, for the memory, for the interaction. So as you can see, this will be the very small numbers compared with the failure and with the distance. However, the units actually we use the gigabytes. Okay, that's why we use the gigabytes, and otherwise maybe dominate. Right. So that's why we use the different unit for this one, and actually we just focus on the maybe when we consider the weight for this part, maybe the dominant one. Yes. So this will be. Thank you for the suggestions. Yes.
Any other question? Right. So if not, let's thank Professor Wen again for his excellent talk. This will conclude our seminar today. Thank you very much. Thank you.